Happy Wednesday, everyone. Thank you for joining our second May webinar. The title of this webinar is Characterizing Viscosity of Bioinks for 3D Bioprinting. This webinar will cover the viscosity measurements on bioink materials and will be hosted by Dr. Sohaila Shabani-Berki. Sohaila obtained her PhD in mechanical engineering at Iowa State University, where her PhD thesis was focused on characterizing the viscoelasticity of hydrogels and complex fluids using colloidal probe microscopy technique. Her work on functional materials has been featured in the Journal of Chemical Engineering Science. Without further ado, it's my pleasure to turn it over to Sohaila.
Thank you, Christian, and thank you for your nice introduction. Hi, everyone. Welcome to the webinar today. I'm Soha, and today I'm going to talk to you about the viscosity measurements of bioinks for 3D bioprinting applications. So let's go ahead and get started. I'm going to start with some quick background about bioprinting techniques so you will understand the nature of the experiments we have done and why they are interesting and informative. In recent years, additive manufacturing has expanded to pharmaceutical, regenerative medicine, and tissue engineering, where it is used to manufacture implants, organs, and drug products. For example, researchers in Sweden for the first time have designed a new bioink that allows a small human-sized airways to be 3D printed by using patient cells. While there is a wide range of additive manufacturing techniques, only a few can be employed for bioprinting of cellular constructs. Of them, droplet-based, laser printing, and extrusion-based bioprinting are the three most commonly used techniques for direct bioprinting, as reported in the literature. And among these 3D printing processes, extrusion bioprinting is well researched because we can fabricate 2D and 3D structures by continuous deposition of a polymer containing cells through a micro nozzle. Typically, extrusion-based printers disperse the bioink using a pneumatic or mechanical system. So this additional system actually helps this technique to disperse high viscous bioink with high cell density. But this technique has a relatively low resolution, which is its downside. Okay, now now let's take a look at the performance comparison between different bioprinting processes. First of all, I'm going to compare the range of printable viscosities that is the main focus of this webinar. Both the droplet-based and laser-based printing systems have a narrower printable range of viscosities compared to the extrusion-based. Additional pressure that is used in extrusion-based system allows the deposition of the more viscous bioinks. Regarding the resolution of each technique, in extrusion-based and inkjet-based bioprinting, the resolution depends on the nozzle size that can be in the range of 20 micrometer to 200 micrometer, whereas the laser-based bioprinting is a nozzle-free system. Overall, the inkjet-based bioprinting has the highest printing resolution. Also, inkjet bioprinting, that is in the category of droplet-based bioprinting, has the highest printing speed, followed by the laser-based and lastly the extrusion-based printing. The deposition or printing speed is critical for large-scale biomanufacturing. So each printing system has its own advantages and limitations over the others. Overall, the extrusion-based is a more reliable and more common method of bioprinting. With that being said, I think now it's clear why it is important to understand the properties of bioinks and how their properties impact the printing process. Basically, understanding the rheology of bioink is necessary for successful 3D printing. All right. Now I'm going to talk to you about the materials that are commonly used for bioink application. Generally, materials for 3D bioprinting are referred as bioinks, which may include living cells, extracellular matrix materials such as hydrogels, cell media, and other additives. A commonly used material for bioinks are hydrogels, and today we're going to focus on this component of the bioinks. This table shows some of the most commonly used hydrogels in 3D bioprinting and their characteristics, such as biodegradability and cell viability, as well as the bioprinting technique that can be used for each material. Some of these hydrogels, as you see, include gelatin, alginate, hyaluronic acid, agarose, Carrageenan, and collagen. The bioink materials should be biocompatible, biodegradable, and they shouldn't have any toxic effect. They also should be bioprintable and enable rapid cell growth and proliferation. EB in this table stands for extrusion-based bioprinting, and as seen, all of these materials are compatible with extrusion-based bioprinting. Now let's take a look at the importance of rheological evaluation of bioinks. Basically, to achieve high printing resolution, shape fidelity, and printing and high cell viability, a bioink with desirable rheological properties is required. And all of these, I mean printability, resolution, and cell viability, are directly impacted by the viscosity of the ink. This figure is an example of extrusion-based bioprinting, showing the Carrageenan properties during the printing that I found in the literature from a paper by Wilson that nicely shows the steps of printing process and changes in rheological properties from the beginning of the process to the end, where the temperature decreases from 37 to 25 Celsius. Depending on temperature, Carrageenan properties can be grouped into sol, shear thinning, and gel behavior. Before printing and in the heated jacket that the temperature is 37, it exhibits sol behavior. Then during extrusion, it shear thins, and after deposition at 25 C, it can be cross-linked and form a gel. Each printing technique is based on different physical and rheological properties of the bioink. During the printing process, imagine extrusion printing, for example, the bioink is subjected to different shear rates. When it is extruded through a small nozzle, it experiences high shear rates. Also, it should have shear thinning property to be extruded through a small needle and regain shape after the deposition. So now I think you understand better why measuring the viscosity of bioinks over a wide range of shear rates is crucial for successful printing. The viscosity of bioink is important not only from printability standpoint, but also it is an important factor for cell viability. In general, bioinks for 3D printing applications that exhibit shear thinning behavior, fast recovery time that could be within 5 to 10 seconds, and presence of a yield stress is typically greater than 100 Pascal, is ideal for 3D printing application. Recovery time is defined as the time required for transition back to the original properties prior to being injected, because after injection or deposition, it is important for the material to regain the original properties. As you know, in bioinks, cells are usually encapsulated or say embedded within a hydrogel. So any changes in the cell concentration affect the properties of bioink. For example, it's clear that higher cell concentration increases the bioink viscosity. So there's always an optimal cell concentration depending on the size of the nozzle and the viscosity of the hydrogel that must be taken into consideration to prevent clogging issues in the nozzle. Besides this, cell sedimentation affects bioink homogeneity and printing output over time, which is a common problem in bio 3D printing. Using Stokes' law, we can theoretically calculate sedimentation velocity, and as you see in this equation, sedimentation velocity is inversely proportional to the bioink viscosity. Now, considering the effect of viscosity on printability and cell functionality, I think it becomes clear why monitoring and measuring the viscosity of bioink is important for 3D printing applications. So with that in mind, I want to talk to you a little bit about our technology that we use for measuring viscosity. Our technology is called VROC technology, viscometer rheometer on a chip. Since we have had full review of our technology in the previous webinars, I'm just going to go over a quick overview of this technology and show you how it works. Our technology is basically a combination of microfluidics and MEMS, or microelectromechanical systems. So we have a rectangular microfluidic channel where we have 4 pressure sensors, which are linearly aligned across the channel. In this system, we control the flow rate through the channel and monitor pressure drop as the fluid flows across the channel. Since we have a well-defined geometry and we know the widths and depths of the channel, we can calculate shear rate from the flow rate and the dimensions of the channel. And knowing the dimensions of the channel and pressure drop, we can then calculate shear stress. And finally, shear stress divided by shear rate gives you viscosity. This is how we calculate viscosity. So we can control shear rate, measure shear stress, and then calculate viscosity. For bioink experiments, we used our fully automated and high throughput viscometer, VROC Initium 1+, that allows us to measure the viscosity at different concentrations and over a wide range of shear rates. So that was sort of the background of what we are going to talk about, and now I'm going to go over the details of the experiments and sharing some data with you. The goal that we have is to show you how we use our VROC technology to measure viscosity of hydrogels over a wide range of concentrations and shear rates. Depending on the sample viscosity, different VROC chips were selected for doing these experiments. For low viscous samples, we can use BO5 and EO2. However, for high viscous samples, it is better to use CO5 and EO2. Having multiple chips, having multiple chips allows us to test a wider range of shear rates using just one instrument. Just a quick comparison. Sorry, Mike. Sorry, just a quick comparison of the chips for those who are not familiar with our instrument. For example, in BO5 chip, the channel depth is 50 micrometer, and for EO2, the channel depth is 20 micrometer. The letters, I mean A, B, C, and E reference the max pressure capability of the MEMS pressure sensors. For example, A chips are able to measure the lowest pressure for low viscosity fluids, and the E chips are able to measure the highest pressures for higher viscosities and higher shear rates. So quality data can be obtained by simply choosing the appropriate chip depth and pressure sensitivity. After this quick review of instrumentation, let's take a look at the materials we used for our experiments. We selected and examined 3 groups of materials that are commonly used in bioprinting. These materials include sodium alginate, the combination of sodium alginate and hyaluronic acid, and copper Carrageenan. Sodium alginate samples were prepared in 4 different concentrations of 2, 4, 6, and 8 weight%, and viscosity was measured using a combination of BO5, CO5, and EO2 chips. For the second set of our experiments, we blended sodium alginate with hyaluronic acid and prepared 5 different combinations and measured viscosity using AO5 and BO5 chips. And for the third set of our experiments, we examined Carrageenan as it shows interesting rheological and biological properties. Despite interesting properties of Carrageenan hydrogel, they have not been explored very much for 3D printing applications. So in this work, we aim to show you its rheological properties at different concentrations. Now I'm going to go over the viscosity data I collected from our VROC technology and share some results with you. This figure shows the shear viscosity as a function of shear rate for 4 different concentrations of sodium alginate. As expected, increasing the concentration of sodium alginate results in a higher viscosity. The highest viscosity data here is around 2800 millipascal second. That shows the capability of our VROC technology in measuring high viscous samples. Also, in all samples, shear thinning behavior are detected, and that, as I mentioned, is necessary for the bioink printability in extrusion bioprinting. Since our samples exhibit non-Newtonian behavior, WRM correction was used to determine the true shear rate and true viscosity. It's been reported in the literature that when we use high viscosity shear thinning materials, increasing the polymer concentration can increase the printed resolution, and it shows better shape retention after it's printed. As an additional analysis, here we used cross-fluid equation to model our non-Newtonian fluid and extract some information about our solution. In this equation, in the cross-fluid equation, eta naught is 0 shear viscosity, eta infinity is low viscosity plateau, and lambda is a characteristic time scale. So the experimental data were fitted nicely to a cross-fluid model, and 0 shear viscosity was estimated by extrapolation. With that in mind, we plotted 0 shear viscosity estimated from cross-fluid model as a function of sodium alginate concentration. With using regression models that are appropriate for the concentration range of our solution, we can calculate intrinsic viscosity. In this study, we use Martin equation as a regression model to calculate the intrinsic viscosity of sodium alginate from 0 shear viscosity data. In this equation, again, eta naught is 0 shear viscosity, eta sub S is the viscosity of the solvent, which is DI water here for our experiment. C is the concentration of the solution, and eta in brackets sub 0 is intrinsic viscosity. The extracted value for intrinsic viscosity from the Martin equation is 5.14 deciliter per gram. That is in good agreement with the most reliable reported data in the literature. After evaluating the effect of concentration, we proceeded to study the effect of pH on viscosity and shear thinning behavior of sodium alginate. This figure shows the average viscosity as a function of shear rate for 3 sodium alginate solutions with varying pH values of 6.1, 5, and 3.9. To adjust the pH, a small amount of hydrochloric acid was added to 2 weight% sodium alginate solutions to drop their pH. So the initial pH value of neutral solution was measured as 6.1. That indicates the dissociation of carboxylic acid groups in the solution. To further analyze the behavior of sodium alginate at different pH values, I would like to mention that based on what I've seen in the literature, viscosity increases with decreasing pH in the low shear rate region. I mean, shear rates lower than 10 inverse second. This behavior is likely due to the formation of hydrophilic hydrophobic aggregates. However, our experiments show that in the moderate to high shear rate region that we examined in this study, lowering pH decreases the viscosity. This trend likely indicates that hydrodynamic forces can disrupt the aggregates and that eventually decreases the viscosity. In another interesting experiment, the steady shear viscosity of the sodium alginate solutions was characterized as a function of temperature. This figure shows the average viscosity as a function of shear rate for 1.5 weight% sodium alginate at varying temperatures of 15, 25, and 37 Celsius. In general, as the temperature decreases, the viscosity increases, and this is advantageous for sodium alginate within the bioink, since the viscosity can change with temperature and it can be more compatible with printing requirements. As I showed in the introduction slides, in some bioprinting processes, the bioink is kept at elevated temperature, say 37 Celsius, to enable the printing process. So this is definitely beneficial. Okay, so sodium alginate obviously shows suitable rheological properties that makes it ideal for bioprinting applications. But based on literature, it doesn't exhibit very good biological properties. For example, it cannot interact very well with mammalian cells. And as you know, cell hydrogel interaction is an important requirement for cellular functions, and sodium alginate does not show very good interaction with cells. Therefore, in order to achieve more desirable rheological and biological properties and to overcome the limitations, new bioinks can be developed by blending various materials. So in this study, we blended sodium alginate with hyaluronic acid to improve environment for cells. Actually, sodium alginate can support printability of the bioink. However, hyaluronic acid can improve the biocompatibility and biological properties. This figure shows the shear viscosity as a function of shear rate for 5 different combinations of sodium alginate and hyaluronic acid. It's clear that the combination of 1 weight% sodium alginate and 2% hyaluronic acid has the highest viscosity, which is around 1000 millipascals second. Again, in all samples, shear thinning behavior was detected. As seen in this plot, the viscosity can be measured over a wide range of concentration and wide range of shear rates, from 40 to around 20,000 inverse second. That again shows the capability of our Vira technology. For sodium alginate, we used a functional relationship between viscosity and shear rate to calculate zero shear viscosity. Here we do the same analysis for the combination of sodium alginate and hyaluronic acid. For these samples, we used Carrageenan model, which is an empirical equation that is used to fit non-Newtonian data. The equation is shown here, where eta naught is zero shear viscosity, eta infinity is low viscosity plateau, lambda is a characteristic time scale, and the exponents a and b stand for power law indexes that typically depends on polymer concentration. So experimental data for the shear rate and viscosity obtained with Vira initium were used to accommodate 5-parameter Carrageenan model. This kind of model fitting always enhances our data analysis. For example, using this model, we can estimate the shear viscosity of our polymeric solutions, or the model output parameters can be used in CFD simulations. With that in mind, now we can plot zero shear viscosity as a function of concentration of our sodium alginate and hyaluronic acid balance. We extracted zero shear viscosity from our model fit and then plotted it versus concentration. The figure in the bottom left shows the zero shear viscosity as a function of hyaluronic acid concentration, where the concentration of sodium alginate was kept constant at 1 weight%. And the figure in the top right shows the zero shear viscosity as a function of sodium alginate concentration, where the concentration of hyaluronic acid was kept constant at 1 weight%. Actually, for single component systems, there are various models, like Martin equation that we use for sodium alginate. There are models that we can fit to our data to estimate intrinsic viscosity. But I think for blended polymers or complex systems, this kind of analysis becomes complicated due to the nature of the mixtures, and it likely depends on how the molecules interact with each other. So far, we haven't done this type of analysis, but I think it can be a potential project for us to focus on these type of complex systems and analyze them in a better way that allows us for a deeper understanding of the structural characteristics of our solutions. Now, let's move on to our last but not least series of experiments. The third bioink that we examined is Carrageenan, that is a polysaccharide derived from red algae. Carrageenan shows interesting properties like it is biocompatible and it exhibits shear thinning behavior. Besides this, it is able to undergo quick gelation or cross-linking process after printing. It shows thermo-reversible gelation, and it also can be ionically cross-linked in the presence of positive ions. So Carrageenan shows interesting properties that I think make it a good candidate for bioink applications. With this background in mind, and now I'm going to share with you some data I've collected for this hydrogel. This figure shows the true viscosity as a function of shear rate for different concentration of Carrageenan, including 0.5, 0.8, and 1 weight%. I think it's not bad idea to share with you that I also made a 2 weight% Carrageenan, but after it dissolved in water, it formed a strong gel and it was not fluid anymore. Based on my experience, I think the critical concentration for Carrageenan is between 1 and 2 weight%. Beyond that, we have a solid gel and we are not able to measure their viscosity. Well, let's go back to this figure. As expected with increasing concentration, viscosity increases and also the shear thinning behavior is detected. I also added an additional experiment so that I prepared 0.5 weight% Carrageenan and 0.1% KCl, potassium chloride, rather than DI water, to see how salinity or ionic solvent affect the viscosity of Carrageenan. In this figure, green rectangles is Carrageenan dissolved in KCl. However, the orange triangles show Carrageenan in DI water. As seen, the plot has been shifted a little bit, showing the viscosity is slightly higher for the sample dissolved in salt solution. However, I think the effect of salt on viscosity would be more pronounced if we increase the concentration of KCl or even do the experiments at lower temperature. Actually, I've done very interesting experiments with Carrageenan to study its salt-gel transition. That can be a potential topic for one of our future webinars. In that webinar, I will share more results and data on Carrageenan, and if you are interested to learn more, feel free to join. So just to quickly summarize before we go over the questions, I just wanted to highlight that we can monitor viscosity of bioinks over a wide range of concentrations and shear rates by using our Rheological Initium technology. So we are able to do this in a fully automated closed system with high accuracy and repeatability. We also see that all 3 hydrogels showed shear thinning behavior, which is compatible with printing requirements. Also, we were able to do further analysis and use model fits to measure zero shear viscosity and use that to estimate intrinsic viscosity of sodium alginate. With that, I will go over to the question section and see if you have any questions. And my colleague Christian, if you can take the questions.
Thank you, Soha. Thank you for the wonderful talk.
Thank you.
So now we will take any questions from the audience.
Okay, so I just mentioned that anyone who signed up the webinar will get a recording at some point. If you have any question regarding this webinar, feel free to contact us. And if you also have initium in your business and you don't know how to make protocols, how to clean your chips, I encourage you to contact us. Our R&D team are here to help you, and we can create cleaning protocol for you or help you to create measurement protocols for your samples. So do we have any questions?
Looks like we have a question.
Mm-hmm.
The question is there any relation between viscosity of bioink versus drying time?
Drying time for can I see? Actually, I don't know what drying time is here.
So it specifies drying time after printing.
Oh, okay. So you mean somehow the recovery time? Actually, I didn't do experiments to explore this to see the effect of the relationship between viscosity and recovery time or drying time. But I think that's a good question. It can be at some point we can explore more this in the future. Now I don't know the answer, and yeah, I cannot answer to this question based on my knowledge. Yeah. Is there any other question? Okay, all right. I think I'm gonna end it today. Thanks everyone for joining us. Every month we have webinar, and if you are interested, you can sign up and join our monthly webinar. Hope you all come back in June. Thank you. Oh, it seems that we have a couple of questions. Oh, okay.